And Dr. Bay, you have, as I said already, you have 20 minutes. And thank you very much for keeping the time. Thank you.
Thank you. First, I want to thank the organizer for inviting me here. Today, my talk is
possible. Speak a little bit loudly. Thank you very much.
Okay. So today, my talk is based on a recent paper with Jiren. Here's my outline. First, I will review some related backgrounds. Then I will introduce a class of analytic solutions of neutral hyperbolic black holes with scalar here. With the black hole, I will show how to calculate the Rényi entropy with a spherical entangling surface. On top of this, I will calculate the entanglement spectrum. Finally, I will summarize our work. So to define the entanglement entropy, we can consider a pure state with two subsystems A and B. They can be described by a density operator rho AB. Then the reduced density operator is defined by taking the partial trace of rho AB. So it only depends on the degrees of freedom of A. The entanglement entropy is just the von Neumann entropy of the reduced density metric. Then as a one-parameter generalization of the entanglement entropy, we have the Rényi entropy, which implies much more information. For example, with the Rényi entropy of all orders, we can determine the entanglement spectrum. Actually, these entropies have considerable applications in many areas. For example, in condensed matter physics, they can be used to detect the topological ordered phases. Besides, entanglement may inspire a deeper insight into quantum aspects of gravity, like the holographic entanglement entropy and the black hole information problem. So how to calculate these entropies? In conformal field theory, we can consider a Euclidean path integral on copies of manifolds that are matched together. It's a so-called replica trick. Then in general relativity, we have the real-Tarski-Anagi formula, which connects the entanglement entropy with the extremal surface in bulk gravity. So these entropies are not easy to calculate in general, but for a spherical entangling surface, they can be calculated by means of a hyperbolic black hole. This approach conformally maps the causal development of the enclosed region A to a hyperbolic cylinder. Then the entanglement entropy can be obtained by the thermodynamics of SFT living on the hyperbolic cylinder. In terms of the ADS-FT correspondence, we can consider a hyperbolic black hole. So the Rényi entropy can be calculated by the black hole free energy. Then the thermal phase transition of black holes is identified with the phase transition of Rényi entropies. Actually, this kind of phase transition of Rényi entropy have been studied numerically in previous work, but here we find an example which is analytic before and after phase transitions. So now I introduce a class of hyperbolic black holes with scalar here. We take ADS4 for example. Analytic solutions of neutral hyperbolic black hole with scalar here is extremely rare, but the MTZ black hole is a valuable solution. We consider a one-parameter generalization of the MTZ black hole. The action is like this. The potential is denoted by a parameter alpha. Different values of alpha correspond to different systems. This potential has some remarkable properties. For example, when alpha takes some values like 0, 1 over root 3, 1, and root 3, they correspond to special cases of STU supergravity. I will explain this later. For now, we just remember this potential can be seen as an interpolation between some supergravity cases. So this solution describes a class of hyperbolic black holes with scalar here, but it does not have spherical or planar counterparts. By this I mean black holes. So the black hole thermodynamics is calculated from standard process. What is noteworthy here is the method by Ko is calculated from holographic renormalization. I want to briefly review this process. To obtain the method by Ko, we need the renormalized on-shell action with a proper boundary condition. So the boundary condition of the scalar field will lead to an additional term in the action. Then the variation of the action gives the energy momentum tensor, combined with the boundary condition we impose, which corresponds to the triple trace deformation in the dual set T. We can obtain the holographic mass. The bico can experience phase transitions. There's another trivial neutral solution in which the scalar field vanishes. It's just the Schwarzschild ADS by Ko. So the hyperbolic ADS by Ko is stable at any temperature, but if we introduce a scalar field to the system, the bico can experience a phase transition to the hairy one. Then this transition can be implied from the IR geometry of the extremal hyperbolic bico, which includes an ADS2 factor. This will leave the BF bound violated. By this, I mean the hyperbolic ADS bico can experience instability even before the temperature reaches zero. Here's some typical thermodynamics of bicos. We plot the free energy as a function of the temperature for different values of alpha. We use the dashed line to denote the S-ADS bico and the solid line to denote the hairy bico. We can see in the second graph that there may be two hairy solutions at a given temperature, which we use the blue line and the yellow line to denote. As the temperature is decreased, there will be a third order phase transition from the S-ADS bico to the hairy bico. It occurs at T0 here, which is 1 over 2 pi L. L is the entangling radius. Then the alpha is between 1 over root 3 and root 3. There will be a zeroth order phase transition from the hairy bico to the S-ADS bico. So the transition temperature is determined by the values of alpha. With the bico thermodynamics, we can calculate the Rényi entropy from the thermodynamically preferred solution. Let's first consider the Rényi entropy without taking into account the phase transition. It can be written as such a simple form. Here, the S plus minus corresponds to the two heavy solutions we mentioned above. Clearly, the Rényi entropy is an analytic function of n with a parameter alpha. Besides, the Rényi entropy from the S-ADS bico are given by setting alpha to be 0. As we mentioned above, there are some values of alpha corresponding to special cases of STU supergravity. By this, I mean the Lagrangian in ADS4 is obtained by reducing from its 11-dimensional lift in supergravities. There are 4 U1 charges here. The special cases is when some of the charges are the same while others are 0. I give some examples here. When alpha is root 3, we find the independence of the Rényi entropy is strikingly simple. It's proportional to 1 plus 1 over n. It has the same independence as the universal result in 2D set T. Besides, when alpha is 1 over root 3, actually in the neutral solution we consider, it's the same as the above case. But since the neutral solution is from the Einstein-Maxwell-Delitzsch system, the 1 over root 3 case is also called the Gibbs-Rocha model in the EMD system with the same potential. The extremal near horizon geometry of its 11-dimensional lift has an ADS3 factor. This may explain its similarity with the result in 2D set T. Besides the alpha is 0, we have the S-ADS bico, but it also corresponds to supergravity. So previous work studied numerical solutions of hairy bicos and Rényi entropy phase transitions. Here we provide the first analytic example of the Rényi entropy phase transitions. Now we use some bar to denote the rate entropy with the phase transition. So corresponding to the black hole thermodynamics, there will be two kinds of phase transition here. For the third order phase transition of black holes, the rate entropy is continuous at the transition point, but its second derivative shows discontinuity. Well, compared with the third order phase transition, the zeroth order phase transition will lead the rate entropy to be discontinuous at special values of n. We can see the two types of phase transition here. We plot the rate entropy as a function of n for different values of alpha. We can see in the second graph that the third order phase transition occurs when n equals to 1 here, and the zeroth order phase transition occurs for n greater than 1. And in higher dimensions, the rate entropy as a function of n can be easily generalized, but it's okay to ignore the details here. An interesting fact I want to talk about is the holographic deal of the rate entropy. By this, I mean the rate entropy also has an area law like the real Tarski-Anagi formula, but the area is for a cosmic brane. So we find in our case that the thermal entropy of hyperbolic black hole is just the deal of rate entropy. So this means the cosmic brane is just the horizon of black holes, but with different temperatures. Anyway, with the rate entropy, we can consider the entanglement spectrum. It's the eigenvalue distribution of the reduced density metric. Let's first assume the spectrum has a continuous part rho bar and a discrete part which was denoted by some delta functions. So the rate entropy can be written as such an integral. Then by reparameterizing lambda to be the exponential of minus t, we can obtain a new integral which is exactly the definition of the Laplace transform. So the entanglement spectrum can be calculated from an inverse Laplace transform. In general cases, we can calculate the entanglement spectrum with rate entropies that are analytic at infinity. This analyticity allows us to expand the rate entropy near infinity as a series. By a previous approach, the inverse transform can be calculated by writing an infinite sum. Here we give more analytic details. First, we still expand the rate entropy at infinity. So the exponential of rate entropy can be divided into two parts. In the first part, we just keep the constant and linear term in the exponential. Then we expand the rest part into a new series. We can write the coefficients of the series by the polynomials, but it's okay to ignore the technical details. Anyway, the inverse Laplace transform is given by the convolution theorem. The results include one delta function determined by the largest eigenvalue and a continuous part. The constant term in front of the delta function is the degeneracy of the largest eigenvalue. Actually, this result has been derived numerically in previous work. Here we give more analytic details by writing its coefficients. Besides, the spectrum are required to satisfy such a normalization, which can be verified in our case. So to briefly review the above calculation, we can just see the box here. Si encodes the data in the rate entropy because it's the expansion coefficients of the rate entropy, and Vi encodes the data in the entanglement spectrum. So to connect them, we can perform an inverse Laplace transform. Their exact relation can be written by the polynomials. Now, as an example, we apply the treatment in supergravity cases. The alpha is 1 over root 3 or root 3. The rate entropy have a strikingly simple independence. So the expansion coefficients only include the first two terms S0 and S1, then the spectrum can be simplified significantly. The continuous part of the spectrum is described by a modified Bézier function of the first kind, and the degeneracy of lambda 1 is just a 1 here. It's the result. It has been derived in 2D FT, but in higher dimensions, the spectrum can also have such a structure. Here's the entanglement spectrum for different values of alpha. And the alpha is in the first graph, we can see the alpha is not extremely close to 1 over root 3, which we denote by the blue line. The spectrum gradually changes with respect to alpha as a whole part. But the alpha is extremely close to 1 over root 3. As shown in the second graph, there's a little difference. The spectral density of large eigenvalues increases with alpha, but the spectrum with small eigenvalues is almost fixed. Besides, the degeneracy of lambda 1 decreases, but its location keeps almost fixed. In the above calculations, we consider the entanglement spectrum from Bai codes. The result can greatly describe the low-lying part. By low-lying, I mean the spectrum with large eigenvalues. But the effect of its transition is still not clear. We can give some observations based on our case. So first, the spectrum near the largest eigenvalue is entirely determined by the large n behavior of the Rényi entropy. Then we use the saddle point approximation to show the spectrum with lambda approaching 0 is dominated by the Rényi entropy with n approaching 0. So for the third order phase transition of Bai codes, the corresponding spectrum with such behavior is determined by the SADS Bai code, because the SADS Bai code is more stable at high temperature. But for the zeroth order phase transition, because of another saddle point besides 0, it's hard to evaluate its effect. Anyway, it would be interesting to see how the phase transition affects the full entanglement spectrum more precisely. To briefly summarize, we have calculated the rate entropies on the entanglement spectrum from a class of hyperbolic Bai codes with scalar here. The phase transitions of Bai codes lead to the discontinuity of the rate entropy and their second derivative at special values n. It depends on the phase transition temperature of the Bai code. Then, from the rate entropies that are analytic at infinity, we calculate the low-lying entanglement spectrum by means of the exponential polynomials. But for the spectrum with phase transitions, what we can see is the third order phase transition will hardly affect the low-lying spectrum, but a more precise analysis to show how the phase transition affects the spectrum is still required. Besides, this work focuses on the neutral limit, but you know the charge Bai code may have more complex phase structures, so it's also an interesting topic to explore. So I guess for the lack of time, that's the end of my talk. Thank you very much for your attention. Happy New Year.
Okay, thank you very much. And if you have any question, maybe you can raise your hand or write inside the chat box, please. Okay, Dr. Bai, thank you again very much for your very nice talk. And we can ask Dr. Narmin Nasibov from Ministry of Science and Education, Azerbaijan, to start her talk, which is devoted to investigate